me start. Hello, everybody. Okay. Hello, everybody. My name is Tian Bai. I'm from UT Austin. And today, I will introduce our work on asymptotic coverage and rate in massive MIMO networks. Here, by asymptotic, we actually mean two things. The first thing is we have infinite antennas in the large antenna array at the base stations. And the second thing is we consider large-scale networks, which has an infinite number of base stations on the plane. And we will use the tool of stochastic geometry to analyze the asymptotic SINR coverage and rate. And here's the outline of my presentation. First, I will introduce some background information and motivate why we use the tool of stochastic geometry. And second, I will introduce a system model, basically how we model the network topology and how we model the propagation channel. Then I will introduce the mean result on the asymptotic SINR and rate analysis. If we look at the figure, this shows the real base station distribution in a US city. And the real base station locations are more irregular than a hexagonal grid. Also, as the densification of the base stations, more and more base stations will appear in a unit area. So to analyze the performance of future cellular network, we need to consider large-scale network with many and irregularly distributed base stations. Massive MIMO is a promising technique for 5G. The basic idea is to have large antenna arrays at the base station, say 100 antennas at the base station, and serving tens of users in a cell. So by serving more users, the cell throughput can be improved. Also, analysis show like the interference and the noise will be reduced if you have large antenna array. So in this work, we will analyze the performance of massive MIMO in irregular large-scale networks. Stochastic geometry fortunately, stochastic geometry is a very useful tool to analyze the performance, the network performance of large-scale network with randomly located points. The basic idea is to model the base station and user location as a certain point process, say Poisson point process. And using stochastic geometry, we can derive closed-form expressions for certain performance metrics, such as SINR and rate distribution. And the stochastic geometry, unlike the simulation approach, stochastic geometry provides a system-wide performance, which is like the spatial average SINR distribution over different user and base locations. And it has already been applied to investigate like heterogeneous network and millimeter wave network. Today, we will use stochastic geometry to analyze the performance of massive MIMO. Talking about the prior work, there are many prior work on analyzing the asymptotic performance in a massive MIMO network, mostly with a few base stations, which we call small-scale networks. And if we look at the result in these papers, firstly they show that even though we have an infinite number of antennas, the SINR will not go through infinity, as a phenomenon called parallel contamination will limit the SINR in the asymptotic case. But if you look at the expressions in their papers, mostly their SINR expression is conditioned on a certain distribution of fixed locations of user and base stations. So if we are interested in the spatial average performance, taking average over all the base station user locations, we need to do multicolor simulation. And the massive MIMO performance has also been analyzed using stochastic geometry. And in this paper, actually, they did not prove the convergence of SINR with a PPP, with a Poisson point process distributed base stations, while the proof of the convergence of SINR with infinite number of base stations is non-trivial. Also, in this paper, he assumed ID fading channel, which ignore the correlation between, like the spatial correlation between different base station antennas. And to simplify analysis, in paper 4, he also assumed an ad hoc type UE and two base station association, which ignore the whenever style structure in the cellular networks. Oh. Okay. In our paper, we developed a stochastic geometry framework to analyze massive MIMO, and we consider like a basic massive MIMO setting. We consider a massive MIMO in the TDD mode, and we model the distribution of the base station as a point-to-point process, and we use the stochastic geometry to analyze the SINR and read the distribution, and we consider both uplink and downlink. And compare it with the prior work, we actually, in our paper, we show the convergence of SINR in large-scale network. And we also consider the spatial correlation between different antennas. Now, this is the basic TDD massive MIMO mode we consider. Like it is operated in three stages. The first stage is uplink training, where all the users send their orthogonal palette to the base station, and the base station uses the orthogonality of the palette to estimate the channel. And here G, the vector G, is the channel estimation, while the H vector is the true channel. As you can see, the channel estimation is contaminated by this sum term, which is the interference channel from other cell users using the same palette, which we call palette contamination. And for uplink transmission, the base station will use the estimated channel, which is G, to do MRC receiver. And this is the downlink SIR expression. And because the channel estimation has error, so there are certain terms in the interference term which correspond to the palette contamination. And similarly, for the downlink, the base station will do conjugate or maximum ratio transmission based on the channel estimation. There will be also an interference term corresponding to the channel estimation error. And here we show the network topology of downlink. Basically, we assume the base stations are distributed as a point-to-point process, which is shown as the black dot here. And we consider there's one typical user, which is located at the origin, and we will analyze the performance at this typical user, which is this very point here. And by using stochastic geometry, we can show that the distribution between the typical user and his serving base station is like ID really distributed. Here is the topology for the uplink. Basically, we consider a dual model of the downlink. Basically, here we place a typical base station at the origin, and we model the distribution of the users as a PPP, point-to-point process. And we assume also the distribution between the typical base station to his serving user are ID really distributed. And for simplicity, we ignore power control in the uplink. This is how we model the channel. We consider there are antennas at the base station and one antenna at a mobile station. So the channel vector H is m by 1 vector. And we consider large-scale path loss and small-scale fading. And the large-scale path loss beta is computed as using the log distance path loss model, which is like d to the minus alpha. And we also consider there's a constant beta, which upper bound the total path loss, which take account like the near field effect of the path loss. And for small-scale fading, we consider a correlated fading channel. Here, the matrix phi is the covariance matrix of the small-scale fading, and W we consider is the ID, like Gaussian vector, which represents like a really fading. We add some constraint on the covariance matrix phi. We assume like the mean square of the eigenvalues of phi is bounded. Intuitively, we just like upper bound the variance of the eigenvalues of phi, which means we consider like there's sufficient scatters in the space such that there's no dominant path observed by base station. We think this is a reasonable assumption for the sub-6 GHz or ultra-high frequency channel. And also this constraint is satisfied by many common models, like the ID fitting model, or if we consider a uniform linear array, where the the angular spread is a continuous range in the angular space. Now we show some our analytical result. The first result is on link level. Basically, we show even though we have correlations in the fading, but if the constraint on the previous slide is satisfied, we still have like asymptotic orthogonalities, like two channel vector. Even they have correlated fading, will still be orthogonal when their lengths become infinity. Next, we show some network level performance. Here we consider when the base station have infinite number of antennas, and we show the SINR, downlink SINR converted to a fixed value, which we call the asymptotic equivalence. And similar to the small scale fading case in the prior work, like even though we have infinite number of antennas, the SNR will not go to infinity because there's some interference term due to the pellet combination will not vanish, even though the M goes to infinity. And another point I want to mention is that showing the convergence in the large scale network is not is non-trivial, because in the large scale network we have infinite number of base stations, so we have infinite sum in the interference term. So to show the convergence with infinite sum, we use the tools in the stoichiometry like the factorial moment. Also, we have the similar result in the uplink, and the result is similar because we assume like the uplink topology is a dual model of the downlink. Based on the the asymptotic equivalent SNR expression, we can also derive the distribution of the downlink asymptotic SNR in a very simple form. So we can save the effort to do monocolor simulation. Here, the expression is only a function of the alpha. Alpha is the path loss, and it is given the SNR threshold t, it is a decreasing function of alpha, which shows that if you have larger path loss of alpha, then the SNR coverage will become worse. If you have larger path loss exponent alpha, the SNR coverage will become better. This is intuitively, this is because if the path loss is higher, then the interference will decay much faster. So we have better asymptotic SNR. And now we want to show some SNR convergence result, like the asymptotic SNR curve is from our analytical result, and the curves for the finite antennas is from our monocolor simulation, and we show that even though we have like 10,000 base station antennas, there's still some gap between the SNR curve of asymptotic SNR curve and the finite antenna SNR curve, and this motivates us to look for the SNR analysis for massive MIMO with finite antennas in the future work. Now we want to compare the asymptotic SNR result with different path loss exponent, as we explained in the previously. Like if you have larger path loss exponent, the SNR coverage will become better because the interference will decay faster. We also compared the asymptotic SNR with the SNR in the Cellular case, and we found that if you have infinite number of antennas, even though we are seeing more user, then we still get much better SNR than the Cellular case. Now we want to compare the rate with like a single antenna cell and a massive MIMO antenna cell. We also simulate the performance of 64 antennas serving 10 users in a massive MIMO network. We also take account the uplink, like the overhead due to uplink training in our computation. Our numerical results show that if we have 64 antennas, then we get like a four times gain in terms of cell throughput. And if we keep increasing the antenna, ultimately we get another five times gain in terms of cell throughput. So this shows that massive MIMO is promising to improve the cell throughput in future networks. To conclude, here we propose a stochastic geometry framework to analyze the asymptotic SNR and rate, and we just derived the closed form expression for the SNR and rate distribution. And by numerical result, we show that the massive MIMO can provide like large gains in cell throughput. For future work, we want to derive like the SNR and rate distributions with finite number of antennas. And we also want to analyze like more sophisticated beamforming schemes. And also we want to look for massive MIMO in higher frequency, like in the millimeter performance. Okay. I also have another one to record. Hello?
All done?
I have another one to record.